Hello, Zentnerds. After the second installment of Alaska A to Z, I noticed that there were several questions on more or less the same topics, so I thought that it might be useful for you if I attempted to answer some of them. If you find this sort of thing helpful, please let me know in the comments. Thanks very much. There were several questions about the Tintina Rocky Mountain Trench Fault, how it formed, what drove it, whether the faults or some other faults caused it to bend, and so forth. So I thought I'd show you a couple of slides of the San Andreas Fault, which is a more recent equivalent of the Tintina Rocky Mountain Trench Fault. Note that the San Andreas Fault separates the Pacific Oceanic plates from the North American plate. The Pacific plate and its captured parts of North America, which include all those rocks west of the San Andreas Fault and the Baja Peninsula, are moving north-northwestwards towards the Aleutian Trench. Whereas North American plate itself, as shown on the right, is moving to the west, or southwest even in modern parameters. So this is sort of the same thing that's gone on since at least 70 million years in North America. The Pacific plates have progressively captured sectors of the North American plate and transformed them to the north. A cool example of what you might get is the Ridge Basin, which is located between the San Gabriel Fault, which was probably an old strand of the San Andreas, and the San Andreas Fault. These rocks were studied by John Kroll at UC Santa Barbara, my old structural teacher, and by many other people because they're so interesting. Here you can see how complex the geology is. This is a cross-section from southwest to northeast. Note that the San Gabriel Fault is the master fault during this time period, which is the late Miocene to Pliocene. And you can see the coarse violin breccia being shed off the fault scarp itself as rocks to the west side of it migrated northward. It was a high-standing block for the most part. Whereas to the east of the San Gabriel is a basin formed. The basin contains tremendous thicknesses of sediment, all studied in great detail by John Kroll, his students, and others, especially oil company people. There's lots of examples of these big faults all over the world, such as the Dead Sea or the zone along the northern part of Venezuela as the Antillean arc swept from the Pacific Ocean into the Atlantic. Well, the main point here is that this process has been going on since at least 70 million years in western North America as the Pacific plates migrated northward and North America migrated westward. So let's move on to the next question, which concerns the 706 isopleth, the 706 strontium isopleth, or 706 line, as people call it. First, we're going to look at what that is, and we're going to do that by talking a little bit about arcs. In 1969, Warren Hamilton proposed that the North American batholithic terrains were formed by easterly subduction beneath western North America, as shown here. Now, one of the things I should break apart and say, there were some questions about why I tipped North America up on its side, and that's because I want to show bigger images on horizontal screens. Remember that all your screens are wider than they are tall, so the slides get a little bit bigger. So if it really bothers you, let me know, but I don't personally have a problem with turning it up on its side, as the shorelines and so forth really don't matter so much. Now, Warren Hamilton had this idea, and it's since 1969, it's been more or less taken as the ruling paradigm of Cordilleran geology. You have a thick Sierran arc based on the thickness, the high-standing nature of the Andes, and the Great Valley sequence out in front of it, a four-arc basin, and then the Franciscan subduction complex, accretionary prism rocks out to the west. And this has continued since 1969 right down to the present. Here's a 2011 figure by Adolf Yankee and others, showing western North America, again tipped up on its side for you. But you can see the Sierra and Batholith, the Great Valley Forearc Basin, and the Franciscan Complex. Now, one of the hallmarks of this is that this subduction flattened and spread inboard, so that the more inner plutons of the Sierra Nevada, for example, came from subduction beneath North America, and the rising magmas melted North American crust to give you some of these easternmost plutons, things like the Sonora, the Tuolumne, the John Moore, the Walt Whitney, the Dome Lands, and many others as well. But these are just the big and best known ones. And these formed in a zone where the arc was really thick, and got hot and started melting the crust itself. And it looks like this in cross section. You'd see that the crust is really thick, you get melting and so forth, and it all rises up to give you these plutons. The problem with this idea is that, in my mind, continental arcs are not high standing. And if you look all around the world, at modern arcs, you'd find that only the Andes is high standing. So let's take a look. If we look at the Cascades, you see Mount Rainier right close to the sea. It's in the Deschutes Halfgraben, as a matter of fact. You can go up to the Alaskan Peninsula. You'd find Augustine in the sea, again, very low standing. Individual volcanoes, of course, can be high standing. Kamchatka, Mount Kluchevskoy, 16,000 feet, recently erupted, as a matter of fact, with that big tsunami warnings that we had now about a month or two ago. And it's again in Big Graben up there and close to sea level. Japan, another example. I've left off Sumatra here because there isn't room. New Zealand, another one. The Taupo zone is actively extending near sea level. The Guatemalan, Honduran Guatemalan, Graben in Central America. Again, you can see these volcanoes in Costa Rica if you've been there. Italy, Mount Etna here again, sitting right next to sea. Here's Pompeii, or one of those ruins there. And I've again left off the Grecian arc. So from my standpoint, virtually all the arcs in the world today are low standing and have to have relatively thin crust, or they wouldn't be low standing. And so using the Andes as your example of an arc is pretty much like using Yao Ming to tell you the average height of the Chinese population. To me, arcs get thick crust when they collide with a continent or another arc, and the lower plate gets pulled beneath the arc. Here you can see Taiwan with the Eurasian plate subducting beneath the Philippine Sea plate in the Philippine arc. And during collision, the buoyant continental plate doesn't want to be subducted. The oceanic plate, of course, driving plate tectonics, and it wants to be subducted. So the two break apart, depending, of course, where that happens. Of course, depends exactly on a number of factors, such as the strength of the plates, the strength of the joins, and so forth. And the lower plate tears away, and you get melts formed as that lower plate gets heated up and melts. The rising melts and the release of the lower plate oceanic slab allow the lower plate to rebound, and it's rising because it's no longer held down by the oceanic slab. So everything gets elevated, and the arc terrain, which sits on top, is rapidly eroded. In many cases, there's virtually no evidence of an arc left. Of course, if the slab break-off occurs at a very shallow level, then the whole origin is narrow, the metamorphism is lower, and you might get better preservation of the arc rocks. If it gets pulled down really deeply, then the erosion is really severe on top, the exhumation and erosion, so you get no evidence of even the arc being there. Anyways, Joe Whalen and I looked at geochemistry of the peninsula ranges in Baja and Southern California, and here's a crude diagram showing the uranium-lead ages of plutonic rocks pre 100 million years, when there was a period of major deformation, which we infer was an arc continent collision. The rocks earlier than that are interbedded with marine sediments, so they were shallow, subsiding, and not thick crusted. Whereas following the deformation, everything was exhumed and eroded. Huge amounts of debris were shed both east and west off to the rising hinterland to the origin, which is nothing more than the core of the origin, where plutons, post-collisional plutons, are in place and metamorphism takes place. The Sierra Nevada, same deal, really. We didn't make quite as fancy a diagram, but we took the work of Beck and plotted it up and got this. So we looked at the geochemistry of pre and post collisional rocks, and we found that we could separate them. Here's an example with strontium, a couple of examples with strontium and yttrium. And we looked at the whole spectrum of geochemistry and found that we could divide the two groups of rocks pretty easily using certain geochemical elements, as you can see here, pre and post 100 million years. But the problem was these are 100 million year old rocks, and we needed some way to test them to see if they were really valid. So we looked at modern arcs and the collision, of course, at Taiwan, and found that, the modern arcs plotted in the arc field that we found for peninsular ranges, and the ones in Taiwan at the northern end plotted in the slab failure field. So the test was pretty successful, and we moved on. In fact, we probably got a little bit ridiculous. We plotted up, here's 4,000 or so samples, plotted up from 3.8 billion years ago to, the present day, and we found that everything held up, and so we argued that plate tectonics was active since about 3.8 billion years ago. Anyways, the important part is to remember that people thought that these break-off magmas, which sit slightly inboard of arc rocks in the peninsular ranges and the Sierras, reflect melting of the continental crust as the eastwardly dipping slab dipped more shallowly, and so involved more mature and more cratonic lithosphere from North America. The problem with that, of course, was shown by Jade Starlacki, who studied the oxygen isotopes in zircons from plutons of the Sierra Nevada. Now, I don't know how many of you know or understand oxygen isotopes. I don't claim to be any expert in oxygen isotopes, but they're widely used nowadays, especially by climatologists. And that's because oxygen 18, O18 if you will, has 2 more neutrons than 16. So it's much harder to, I don't know how much harder, but it's somewhat harder to evaporate than oxygen 16. So in the tropics, when you're evaporating water, you preferentially enrich atmospheric humidity by oxygen 16. And as those waters move northward, rain keeps falling out. More oxygen 18, because it's slightly heavier, falls to the ground than 16. And you can actually measure this. People do. And by the time you get to the Arctic, the waters are pretty depleted in oxygen 18. And so it's used as a temperature or a latitude proxy, this ratio. One of the interesting things is pretty cool to me, anyways, is that big hurricanes basically rain so much that it pulls all of the oxygen 18 out of the atmosphere, and so it gets the air gets completely depleted in oxygen 18. Now, in terms of geology, the oxygen isotope ratios tell you whether rocks have seen atmospheric or meteoric water close to the surface, because of course the values are much higher in oxygen 16, as we've just discussed. So in the Sierra Nevada, this diagram's tossed up on its side again, and you can see the arc rocks, the Stokes Mountain Complex in the lower right. They're quite low in terms of oxygen isotopes. Del 18 we call it, which is the change in 16 to 18 ratios. And those to the east, to the Sonoran intrusive complex, the Tuolumne, the John Muir, the Whitney, and so forth, also have very low values. So they're indistinguishable in terms of oxygen, and they are not crustal values. If you're melting the crust, you're melting sediments. Those sediments have upper crustal and meteoric water signatures because, of course, they were close to the surface. So these rocks were not derived from the crust, which is interesting because they're quite different in terms of many trace elements from each other, but they're both derived from the mantle, not the crust. And you can show that using oxygen isotopes, and that's what Jade Star did. The other thing that's really interesting is when you look at the strontium and neodymium, their samarium neodymium decay group and the rubidium strontium pair shown on the x-axis here show that arc rocks tend to be above 0 in terms of epsilon neodymium and have lower initial strontium values, which is the strontium value at the time the body was formed. So you need to know the age in order to calculate the initial 87-86 ratio for strontium. But anyways, the post-collisional rocks are more evolved in terms of strontium. In other words, they have values of 7055 and greater, and they're shown in red on this figure, whereas the arc rocks, which are lower in strontium and have more primitive epsilon neodymium values, are shown in green. Arc rocks all over the world plot above 0, or CHUR, which is a chondritic uniform reservoir. It's a primordial reservoir of neodymium. Anyways, they all plot above, as does the mantle peridotite and so forth. The rocks of the mantle are all up there close to Morb at the very, very top of this diagram. So you can show that the strontium 706 strontium isopleth is more a function of whether the rocks are slab break-off rocks or arc rocks. Now they differ in lots of geochemical attributes like we saw, but they're all from the mantle. And in fact, I've shown in this figure some big purple crosses. They're garnet peroxenites, also mantle rocks that have come up from the mantle in diatremes at younger periods of time. And also Snake River Plain basalts are shown in small black crosses. All of these have the same initial strontium ratios as the post-collisional rocks in the Sierras and the Peninsula ranges. So the 706 line doesn't necessarily have anything to do with crust, although it does have something to do with cratonic lithosphere, because in our mind, the rocks come from the mantle, but as they rise through the thick mantle root of old cratons, they get a different isotopic signature. So the 706 line is more related to slab breakoff than arc magmatism. And of course that leads to all kinds of interesting things, because in the case of North America at 100 million years was migrating westward as the Atlantic Ocean, still migrating westward actually as the Atlantic Ocean opens. So as these magmas rose from the mantle, from the slab, they arose farther and farther east into North American lithosphere. So, the 706 line does measure something. It does measure whether you have old enriched subcontinental mantle lithosphere. If you went to the Coast Plutonic complex and looked at the slab breakoff magmas there, they don't show this. They plot with arcs because, of course, there's no old and enriched subcontinental mantle lithosphere there. So the 706 line needs to be treated with a grain of salt. So what Joe and I did, we said, wow, okay, these rocks are all from the mantle. How much crust can be involved in these rocks? So we plotted up crustal arc rocks, arcs that pass through continental crust, and compared them to arcs that didn't pass through continental crust, just came up through oceanic lithosphere. And we found that they're basically the same. They fall in big balls here, as you can see. You can pause and study this figure. You'll see that there's both continental and oceanic arcs. But in terms of elements such as rubidium, strontium, zirconium that are enriched in continents, there's not really much difference. There's just a big blob. So the 706 line is probably not what it is reported to be, although it's quite useful, or it can be quite useful if used judiciously. I'll end with one of my mottos.